We're going to talk about the electric field of point charges and parallel plates. Every charge has an electric field that surrounds it and exerts a force on all other charges in the field. This field expands radially and goes throughout all of space. Now we can model the strength of this electric field using the equation E is F divided by Q, with F being the force applied on a test charge and Q being the magnitude of that test charge. And this is measured in newtons per coulomb. Now an electric field shows us how a point charge responds when a positive test charge is placed in its vicinity. A negative point charge will attract a positive test charge to it. Now a positive point charge will repel the positive test charge from it. And this is how those two look when they are in isolated electric fields. Now, in order to determine the strength of the electric field, we can use Coulomb's law, where the force of the electric field is equal to K, Q1, Q2, which is the magnitude of the test charge, over R squared. Now, using the equation we just learned, E is equal to the force of the system divided by the magnitude of the test charge, we can sub in F to the value F in the second equation and get that the strength of the electric field is equal to K Q1 over R squared. And this is how we determine the strength of an electric field. An important concept to note is that if an object is at the same radius from the point charge, it will have the same strength of electric field. And this goes for all objects at the same radius. Now let's talk about the interaction of multiple point charges. If we have two negative point charges, they will both try to attract a positive test charge, and therefore they will both have fields that point inward towards the point charge. If there are two positive point charges, both of them will try to repel a point charge away from it. And in the middle here, for both of these, if there are two negative point charges or two positive point charges, there will be an electric field value of 0 for the middle here, as both of these will try to pull away with even force, and in this scenario, both of them will try to attract the positive test charge to the point charge with equal force. Now, if there is one positive and one negative, the point charge will be attracted to the negative point charge, but the positive point charge will repel the positive test charge closer to the negative point charge. So this means that this negative point charge and positive point charge electric field system will have a greater strength than just the negative point charge alone. And that's all for point charges. Now let's learn about parallel plates.
Next, we will discuss the electric field between two parallel plates, which has a very interesting property. Given a few assumptions, everywhere in between the two parallel plates will have a constant electric field strength. Let's say we had a positively charged particle. It would be repelled from the positive plate. It would be attracted to the negatively charged plate. On the other hand, if we had a negative particle, it would attract to the positive plate and repel from the negative plate. There are three assumptions that need to be made in order for this to apply, however. First of which are that both plates must be of different charges. Let's say that there are two negatively charged plates. A positively charged particle would be attracted to both plates with an equal force, which would cancel out and lead to a net force of 0. The second assumption that must be made is that both the plates must have an equal distribution of charge. Let's say this negative plate had an unequal charge on the left side. There would be a much greater force on this left side than the right side, which is an unequal distribution of force. The final assumption that must be made is that the far from edge rule applies, which means the two plates extend infinitely in all directions, both length and width. This prevents any curved electric field from occurring at the edges of the plates, which would also lead to an unequal distribution of force. In order to calculate the electric field strength, we can use the equation electric field strength is equal to voltage over distance of the two plates. So how does volts per meter relate to the newtons per coulomb that we saw in the point charges part of the video? Well, let's say we multiply both sides by meters. Newtons times meters is equal to joules, and then we have divided by coulombs, per meter. Now joules over coulombs is actually equal to volts, so we have volts over meters, which is where we started. In order to calculate force, it is actually calculated the same way point charges are calculated, where force is equal to the electric field strength times the charge of the particle. Now, we will talk about gel electrophoresis.
While parallel plates have many important real-world applications, one of the most interesting is in forensics and biology through the process of gel electrophoresis. In a gel electrophoresis tank, two parallel plates are hooked up to a power supply, which creates an electric field through an agarose gel which holds one or more DNA samples. Each DNA sample consists of many small pieces of a DNA strand that has been broken up by restriction enzymes, and because all DNA contains a phosphate backbone, it has a slight negative charge, meaning each fragment acts as its own negatively charged particle. The interaction between the electric field and the DNA fragments pushes the fragments through pores in the agarose gel, which creates distinct visible bands. And, using Newton's second law, we can determine the band that's separated by their mass, with larger fragments, which are more massive, staying closer to their starting position, and smaller fragments being accelerated faster and therefore moving further through the gel. This can be used to compare the similarity of different samples, which has many applications, such as comparing suspects to a crime scene sample, or comparing potential parents to a sample of a child's DNA. For example, in the gel I've drawn here, we could determine that the orange and yellow samples are more likely to come from the same or similar source due to the similarity in the bands that they produced. Thank you for watching. We hope you've enjoyed learning about point charges, parallel plates, and their real-world applications with us.